At this moment, I am going to be speaking strictly about what we see when we look through the Minnesota VDL keyhole, and we can discuss whether that's really something that is representative or not. So just to break the ice, I was thinking that in terms of how to present this talk, I would say that currently in the world in which we live in, it's certainly an exciting situation in which things come and go fairly quickly, and infectious diseases are no different, so some problems emerge, some others faint, and it's true that at some point one wonders how much things are changing really now compared to before, or it's just that we have more data now, and now we can basically track those things. So perhaps many of the things that we are looking at now, they were already dynamic before, but we just didn't know. So at some point, it's true that I would like you to have in mind throughout all this talk how many problems are we having now interpreting this data, just because the data is there and perhaps it's not making that much sense. So Salmonella is a very good example on how difficult it may be to interpret some of the data, as it was brought up in the talk before. I was thinking of it as a moving target, right? So the fact that it's still so important, even though we have known it for so long, and we know that it's one of the most important foodborne zoonotic diseases, it's because it has a very complex epidemiology. So even though it's creating a big economic impact in many countries around the world, we still can't manage it very well, probably because there are so many reservoirs that can act as potential sources of infection for humans, and that includes food animals, companion animals, contamination of other food and feed. And actually this has led to this stable incidence. So this is the data on incidence of different foodborne diseases here in the USA. And what you can see is, while if we compare the data recorded in the last 15 years with what we had before, for some diseases we have reached some kind of progress. In terms of Salmonella, which would be this red line, the trend is almost constant. So we haven't really made much progress, and it's really hard to actually make a change in terms of the incidence in humans. So what do we mean when we say Salmonella? So it has quite a challenging taxonomy. There are 2 species, 6 subspecies, over 2,500 serotypes, but most of the time we are talking about just a few, which are the most important ones. And as also Dr. O'Connor brought up before, we can see changes if we try to track down the changes in serotypes over time. Now, those changes may be due to actual true differences that happen in the population out there, or it may be also due to reporting changes, such as, for example, this decrease that we see in the number or in the proportion of cholera suis that were typed at the MVSL 20 years ago, I guess. It may be due to a true decrease in the prevalence of Salmonella cholera suis that was also coupled by an increase in other serotypes, mainly Typhimurium, but also because perhaps people were submitting less samples of that particular serotype because they could identify it without actually submitting the sample to the MVSL. So that's also the same, of course, in humans, and here you can see how, in terms of human incidence, we have enteritidis and Typhimurium, which are the top, and then we have a bunch of others that are changing over time. So we have some that achieve certain peaks over time, but then decrease again, such as Heidelberg here. And the one in which I would like to focus here is this one, the 4,512I negative, that I'm going to call monophasic, because that name is too long. And you can see how also in humans it has gone from virtually inexistent to actually becoming a fairly important one, so that in the last years it's being consistently found among the top 5 serotypes in humans. Actually, it's number 5. So what is that serotype? Dr. O'Connor mentioned a little bit about it also in her talk before. Basically, it's a Typhimurium variant that does not express the phase 2 flagella. It was rarely reported before the 90s, and that may be also up to a point, to a certain degree of underreporting, but it has become emerging since then. So since the late 90s, when it started to become a hot topic, now we see that actually in the US, as I mentioned, it's among the top 5 serotypes from human clinical cases since 2011, accounting for over 5%, which is a fairly significant number, I would say. And in Europe, it's exactly the same thing. So it increased over the same time frame, and it's now the 3rd most common serotype, and it accounts for over 7% of all human cases that are notified there. What is the origin? So where does this come from, right? We're seeing it in humans. Where did it come from? So basically, it's traditionally linked to Salmonella Typhimurium. It has a very similar antigenic formula. And what's the animal source? So it has been isolated multiple times from different food animals and companion animals. But the pigs, it's of interest for us today probably. And it's actually one of the most commonly associated host species with this serotype. In 2011, in a study, they described it as the third most frequent serovar recovered from swine. And however, this is not so much picked in the NARMS data, such as the Dr. O'Connor said, so you do see some increase, but it's still below 2% or 3%, so it doesn't become so evident when you look actually at the samples that are collected at the slaughterhouse. So again, it has been reported as the causative agent of several large foodborne outbreaks. Probably all of you remember the one in Washington State last year in 2015. So no wonder that it's actually an important foodborne pathogen. So what is that? When we say a 4,5,12I negative or a monophasic, what are we meaning? Well, we are talking about something that regardless how you look at it, regardless the technique of the lab that you use to study it, it's going to be somehow closer to a Typhimurium than anything else. So it's kind of a Typhimurium variant, no wonder. But still, if you look close enough, you can see some differences within this serotype. So there are some strains that belong to these serotypes that are different from others. And that, of course, depends on the technique you are using. And depending on different molecular techniques, you can hear about Spanish clone, that it has a certain antimicrobial resistant profile, a European clone, which is typically found in swine. And that has suggested that perhaps what we have is, for whatever reason, multiple independent emergence events, so multiple Salmonella Typhimurium over time are undergoing certain changes and are now expressing this particular antigenic formula, and it's not just one single clone. And then we have the antimicrobial resistant layer of complexity, so that's of course a hot topic, and that makes everything a little bit more interesting. So this particular serotype has been frequently associated with resistance to a number of antimicrobials, most commonly this profile, ASSUT, which would mean resistant to ampicillin, streptomycin, sulfonamides, and tetracycline. And you can see here the proportion of strains of this particular serotype, of this monophasic, that are expressing resistance to different antimicrobials. And I didn't put the legend, but you have to believe me here that these 4 lines actually each represent one of those antimicrobials. So we see that since 2007, 2008, actually the proportion of strains that get to the CDC, so they come from human clinical cases, that are showing resistance to each of those antimicrobials is increasing significantly over time. So it means that this is the phenotype that is, the combination of the resistotype that is actually getting to the human population, the clinical population. And again, this 2015 outbreak, actually only a subset of those got typed according to the CDC report, but all of those that were tested for antimicrobial resistance were expressing this same resistance pattern. So, at this point, what we're wondering is, can veterinary diagnostic laboratories help? I'm very happy of having listened to the previous talk, because most often I spend most of the time trying to convince people that actually there is some value in using those data in spite of all the biases that, of course, we know are there. So we acknowledge those biases, we embrace them, but we still think that there may be some value in this data. And I hope that you are already half convinced after listening to the previous talk. So, in fact, actually, in the past, the MVSL data was also reported in the NARMS until 2006, and of course, I can see why you would discontinue that and not consider it representative or informative when looking at the risk for the human population. Of course, those data would be representative of sick animals that, by definition, shouldn't enter the food chain. You really are never sure about what's the true status of that animal. Okay, it's sick, but what kind of sickness, what was the process that actually drove that sample submission. And so therefore the point would be that if this is the farm and I want to know what's going on here, if I look at the VDL data, I'm just looking at this sick animal at some point and I really don't know what's going on around. And I think that's a very valid point, and that's a very valid concern. Still, in spite of this, I would say that the sick animals are part of the herd of the farm at some point, so they may represent a source for other animals, and they are at least telling you something about what happened at some point in the farm. So we think that, yeah, okay, it's true. It may not be the best thing to do, but if the data is there, it may help you to learn a little bit about what's going on. So our hypothesis is that actually looking at the VDL data can help us to get a better understanding of the Salmonella ecology over time in pigs and detect differences in trends. So we are not saying we are going to know exactly how the weather looks like, but what we're saying is that perhaps we can see if, looking at through this keyhole, we can see if there are big clouds or if there is a storm coming, even though we may not sure about the temperature. So still, I would like for you to bear in mind that we don't want to overestimate this data. Again, I cannot stress this enough. We have to be careful about the reasons for submission, what's the actual origin of the sample. Sometimes it's really hard to track back the sample to the actual farm due to many complications in the labeling of the samples. What's the clinical significance of the isolate? The fact that you get a salmonella from a pig sample, of course, it doesn't mean that the pig was sick due to that salmonella. And in addition, I'm gonna be talking a little bit about antimicrobial, and then we cannot extrapolate this data to the impact on food safety and on humans, because actually the panel of antibiotics that they use in NARMS is not the same that we typically get for food animal isolates. So the objective is to explore the usefulness of the VDL data, using just the Minnesota VDL data as an example, to detect changes in the ecology in terms of serotypes, AMR profiles of Salmonella in swine. And I promise I will be going back to the monophasic very shortly. And the point would be that we can expand this to other pathogens. So this is the data, actually. I don't have as many isolates as Dr. O'Connor had, but I do have 2,600 isolates to talk about that were recovered in the last 10 years. Why are we selecting this time frame? It's also a little bit artificial, but talking with the professionals from the VDL, they suggested if you consider this time frame, you are, comparing apples with apples. While if you try to go any further in time, I may not be that sure. So that's why we're focusing on this time. So we get on average between 180 and 384 isolates per year with a mean of 280, and they overall came from 1,800 animals. So we did a little bit of processing in order to exclude those isolates that we were recovering consistently from the same farm within 1 month that were having exactly the same serotype and the same AMR profile, assuming, okay, this is just the same strain that we are getting it from multiple animals, so I don't want to overcount that. So we would count each of those just one time, and we end up having more close to 2,500, 85% of which were recovered from tissue and 15 from fecal samples. Most of them were serotyped successfully, and I would be happy later to explain how we do serotype, why do we serotype isolates at the MVDL, if I understand correctly, but thankfully the director of the VDL is here, so he may prove me wrong if I don't know. And then we ended up having 79 serotypes, so all these strains belong to 79. Which serotypes did we have? Well, not surprisingly, also very similar to what you could see in the ISU data. We had the Copenhagen. Actually, we could break it because we are not comparing with anything else. So the Copenhagen was not, well, the bar 5 was number 1 with 21%. Then we have 15% of Agonas. Then came Derby, then Typhimurium, the classical Typhimurium, and then the Heidelberg. Now, if you look at the changes over time, this is of course dynamic, and you see that even though the most common has been traditionally the bar 5, now it's getting a little bit less frequent, and Agona is increasing and going from traditionally number 2 to number 1 in the last years. Same deal with number 3 and number 4, you see some changes up and down, and the interesting one is this one, the black bar, which is the monophasic, that again also in this database goes from virtually inexistent to, it's kind of there, and to be consistently increasing in the last 4 or 5 years. And it would be mixed here in this 29% of other serotypes, but actually last year it was the 3rd most frequent serotype. So this is a comparison of the NARMS data. Since you have heard of this enough, I'm not going to get into details, but just you can see how different the profile, so this would be the most frequent serotypes that you get when looking just at the isolates recovered from the slaughterhouse. So this is excluding any kind of clinical isolation, just from healthy animals. And you can see how different the profile is, the most common serotypes, compared with this one that has the serotypes in the same order as this one. But you can see that here, for example, we have Agona that was not that frequent in animals at the slaughterhouse. And again, the 4,5,12I negative that here is even less frequent. So what's the reason for that difference? Well, of course, we are talking about different animals, so no wonder you get different strains. That's perfectly assumable. And that may be even more true for the monophasic, in which we actually looking detailedly with the help of Dr. Banucci at the case reports. What we found is that actually 34% at least, you could be quite certain that in those cases the clinical picture was due to the monophasic isolate. So what do we know about AMR trends? Here it's the graph showing you the prevalence, or I would rather say the proportion of resistant strains over time. And I'm talking here about all Salmonella, so not the monophasic. And you can see how this changes for the different antimicrobials. I don't want to get into details here, just tell you that for many of them there was no change over time. So if you were in 70%, you ended up in 70%. For a few of them, you did see some nice change, what we want. We saw a decrease in the proportion of resistance, but always fairly modest, and this would include ampicillin, ceftibufir, florfenicol, and oxytetracycline. But this would be fairly modest, again below 8%. And one of the things that was kind of annoying or not so concerning, I would say, was the increase in the resistance to enrofloxacin that came from virtually 1% to right now, well, in the last year, around 18%, which may or may not be, but I would probably put my money on that bet, that it may be related with the licensing of the enrofloxacin for its use in swine in 2008. And we can see how the percentage of resistant strains has increased consistently. We're still below 20%, but in clinical samples recovered at the VDL, so a really biased population, but I would assume that the bias is probably holding over time, it seems to be there. You can't really miss it. What if we look at the MIC level? I would assume that everybody knows what an MIC is, basically the concentration that inhibits the growth of a bacteria. So if we look, instead of looking at the whole percentage of positive versus, resistant versus susceptible, we look at the concentration of antimicrobial that actually inhibits the growth over time. We see that for enrofloxacin, if we look at the comparison that I was doing before, resistant versus susceptible, we'll be looking at just this line. So this is marking how the proportion of susceptible strains is decreasing, because this is our threshold, 1 microgram per milliliter, and it goes from 0 to around to about 85-80% of susceptible strains. However, if we look at lower concentrations, we see that the proportion of strains that would be considered susceptible or whose growth would be allowed by lower concentrations is also decreasing, which means that what we're seeing seems to be a fairly consistent trend, and that I would assume that it doesn't have to necessarily stop just by itself. What if we look at the trends in terms of serotypes? We see that also the resistance is not the same across serotypes. And here you can see for each of the antimicrobials the proportion of strains that were resistant of the most frequent serotypes plus the monophasic. And I just want to focus in these two, which would be ceftibufir and enrofloxacin. Why? Well, enrofloxacin because it's concerning, and we see that actually among those top serotypes, it's particularly the monophasic and the agona, the ones that are showing the highest proportion. Always not very high, always below 20%, but still significantly higher than some of the other predominant. And also for the ceftibufir is the other antimicrobial in which our monophasic strain has a significantly higher proportion of resistance compared of his or her cousins, the bar5 and the classic Typhimurium. So at this point, what we are making ourselves, the question that we're making ourselves is, okay, where is this coming from, right? So is this one successful clone or multiple clones that are emerging from different Salmonella Typhimurium strains, what we're seeing here at the Minnesota VDL? And in order to answer this question, with the collaboration of the Minnesota Department of Health, what we have done is use whole genome sequencing to first compare a subset of the monophasic strains that we got, that included 48 monophasic strains recovered from swine in 2014-2015, plus 3 non-swine strains, 2 from bovine and 1 from turkey, all from the Minnesota VDL, and 179 Salmonella Typhimurium, half of which were isolated from swine, and 201 bar5 Salmonellas, 70% of which were isolated from swine, that also came from food animals at the VDL in 2003 and 2012. So what we are assuming is, okay, we are sampling more or less the same animals where this population are, where these bacteria are coming from, and we want to see how similar these bacteria are. We know that they shouldn't be too dissimilar because they're kind of distant cousins, but we want to know how similar they are to see if actually there is more relationship between certain monophasics and certain Typhimurium, or all monophasics would be clustered together. And then in a second stage, what we have done is compare this set of monophasic swine isolates, plus these three actually, with all the monophasics that had been sequenced and whose data were publicly available. So we have collected all the monophasics that came from, most of them from the US, but a few from outside the US, from food animals, from human cases, from food, and we have compared them to our Minnesota monophasic strains. What do we see here? So basically here you see a tree, and I don't want to get into the details, but just to show you, in the red color you would have our 4,5,12I negative strains, which is just 51, and the Typhimurium would be in green, and then in blue you would have your bar 5. And then the asterisk would indicate the swine, the isolates that were recovered from swine. So we see that first of all, the monophasics are clustered very clearly apart from any other strain, just this small cluster of Typhimurium, most of which interestingly come from swine. Then we have this A here that I am developing a little bit more here that you see that is formed by both Typhimurium and bar 5s from multiple species, but only a few pigs, and we have incidentally one monophasic here, which would be one of the ones that were not from swine. This one is from cattle. And then we have this one here that I'm expanding here, which would be our swine clade. This is our swine Typhimurium bar 5 clade, and that it's way far apart from our monophasic clade. Okay? Now, what if we compare just our monophasics with all the monophasics that are out there? What do we see? Basically, we see, first of all, this kind of shape, this kind of topology. The colors here indicate the ones that were recovered in the USA. The red would be USA, 422, so most of them. And the blue would be the ones that are not coming from the USA, that are just 94. And we see, first of all, that we have two clearly separated clades. And both of them, they include strains that were coming from both, that were recovered from both in the US and elsewhere. So this is still preliminary information, but this topology seems to be fairly well supported by the analysis. And with the asterisk, you can see the VDL data, and you see that actually most of the VDL are in this clade, with just this one that again is that cattle strain that was also somewhere else in our Typhimurium comparison. So most of them would be belonging to this clade too, just for the sake of a name. Now, how important is this? Why should we care about this? Well, one of the interesting things that we have done is look for resistant genes that could explain a phenotype of resistance to certain antimicrobials. And what is interesting is if we try to describe, or if we try to find the genes that would yield a ASSUT, that phenotype that I said before of resistance phenotype, we see that actually it almost perfectly correlates with our clades. So all this big clade, what I named clade 1, it doesn't have the full asset, it doesn't have all the genes, may have 1, 2, or 3, but not the 4 of them. And in this case, most of the ones that are included here would have that. And here again, the asterisk is indicating the swine, so we see that most of the swine that we have, both from Europe and the US, would be in this second clade. Interestingly, among other genes that we found, in the 51 isolates from the MVDL, 13 of them were resistant to enrofloxacin, so would belong to that 10 or 15 or 20% percentage that I mentioned in one of the first slides. And in all of them, we found QNR resistant genes, which are, it's kind of a cause of concern because those are plasmid-borne, so those should be fairly mobile. And we found them in all those strains that were showing a resistant phenotype. So, in order to conclude, because I think we are more or less good in time, these are my bullet points. The first one would be the frequency of isolation of this particular monophasic strain from swine clinical samples. So again, keeping in mind all the limitations and all the biases associated with our sample. It has definitely increased since 2011, becoming the third most common in 2015. Then my second point would be that according to our analysis, these strains don't seem to be closely related with other Typhimurium strains that are circulated in food animals, and I would say with the vast majority of strains that we recovered in the VDL. One important point that I don't think I've stressed enough, we don't have exactly the same time coverage. So for our comparison, it was 2002-2013. For our monophasics, it was 2014-2015. These kinds of things that happen in reality, but still, that's what we're getting from the tree. Now, third point would be that our monophasics are divided in two clades, with most of the US, and non-US actually, but since we have more US, most of the US swine isolates located in clade 2, with human cases located in both clades, so we're not saying that this is basically where all the human infections are coming from. And then the fourth one, very important too, is that the resistance to enrofloxacin in swine clinical Salmonella isolates recovered at the MVDL has been increasing since 2008. And in at least a subset of isolates, we know for sure that it seems to be mediated by plasmid-borne QNR genes. So, what are the next steps that we are trying to focus on? Well, one thing is trying to learn, understand a little bit why is this strain becoming a predominant strain through metabolic modeling, trying to see what does make this strain different. Second one would be try to characterize what's the mechanism behind that increase in enrofloxacin resistance in other serotypes, in addition to what we know already from the monophasic. And then the third one, and this is through some projects that we have funded at the University of Minnesota, how we can combine data on IMR with information on clinical significance and antimicrobial use at different levels to try to understand a little bit better how this system is going and why we are receiving these signals.